So now that we actually have our model up and running and we're able to train it and save some weights to this 5k predictor.model file here, now we will actually look at what the loss numbers are and how we can improve that. So first of all, let's see what these actually mean. So the regressor model that we used uses root squared mean error by default. So what that means, these numbers here, these are actually in seconds. So it's hard to see without commas. It's about like 13 billion seconds or so, but remember that's squared seconds. So we would take the square root of that, which is still about 100. I did it on a calculator here. Yeah, 116,000 seconds, which is still a long time. That said, the fact that these loss numbers are going down every iteration, that is what shows you that the model is actually learning because the error is decreasing each time. So those error seconds goes from 135 billion squared seconds to 123 billion and down to about like 83 billion squared seconds. So that means that when you take the square root of that to get the seconds, that's going to be smaller. So the error is going to be smaller and smaller each time. Granted, these are still very large numbers. So when the numbers are so large like this is where I was talking about earlier. This is kind of a trial and error to figure out like what hyperparameters to choose. Often when the training loss is this high, it points to two likely causes: the hyperparameters or the data quality itself. And that's what I want to talk about in this video to figure out what we can do. We know from many previous videos that this data is not the greatest. I have a SQL query that I open up here, and basically what this is going to do is it's going to order everything by the deadlift. So everything that has just an extremely high deadlift number is up here on top, and you see you have many people who are in the thousands of pounds. So what I want to do is I don't really want to include that because that seems like either an outlier or they're Superman or I don't know what. So what we're going to do is we're going to come down here, and so this code is basically going to be my code to look at just some outliers, just basically limiting the data frame to only be numbers that are actually feasible. So for like deadlift, I don't want anyone under 150 pounds, and I don't want anyone who does over 700 pounds. There definitely are people that do over 700 pounds, but not not many. I'm also going to put in this print statement because I'm interested in seeing how many athletes we filter. So I've got the length of the athletes up here, and then after filtering outliers, we'll see what it is down there. And we'll see how that affects our training as well. So if we run it again, oh, it's because this extension that I use, I have to close the file. I think that should do it. There we go. Okay, so you see that the training loss has gone down significantly just by doing that. So what did we lose here? We lost, it went from 17,000 athletes to about 16,000 athletes. So about 1,000, a little bit over that. So it's not that. We still have a lot of training data that we can use, but this takes out those extreme outliers that were dragging the loss many different directions. So after looking at the data a little, now we can look at the actual hyperparameters. So the most obvious one to test here with is the number of iterations. So 10 iterations is pretty small. So you see that the loss is going down by a fair amount each time. So we could just increase that, but we'll save that for later because obviously more iterations is it's going to take longer. So instead, let's look at the learning rate here. Let's see first if you try to set it to something high first, like 4. That I'll explain what it means once we run this. All right, so you see that, oh, now the numbers are actually going up. So what's happening here is that this learning rate of just 4 is very, very aggressive. So you can think of the learning rate like the algorithm taking a step every iteration. So it's taking steps. Think of it like a valley. So it's taking steps down one side of the valley, and if it's taking steps at 4, those are very large steps. So it's taking one step, it's going about to the bottom, and then it takes another step. It actually steps over the bottom of the valley and onto the other side and starts going up the other side. So that's what the danger is with a very large step like that. You can think of it like that. So conversely, if you make it very small, if we make it like 0.1, then let's see what happens. Then the training loss, it goes down at a lower rate. Let's make this actually even smaller. Let's do 0.001. And you can see the learning rate actually, it is going down still. It's going down very, very slowly though. So this is kind of the whole trial and error thing. For our data set, I've found that it seems like the sweet spot is about like 0.4. So if we try that, then you start at 38,000 and go down to about 31,000. I do want to go over another hyperparameter that I can use, but before that, I want to show another evaluation metric. So the R2 scores are important because they help explain the variation that you get in data. So let's just see what this is right now. So we run training.py. With the values that we have, it's explaining about 29% of the variation in the test data and about 33% in the training data, which is it's not horrible, but it's also kind of healthy because you want these two numbers to be close together. So let me show you what happens if I use another parameter. So gradient boosting regressor is what's called a tree regression model. So it works on a series of decision trees. So you can kind of think of that like a series of if statements, like is age less than 30? Yes, then ask is your deadlift over 200 pounds? Yes, then move on. And etc. like that. So I know that's not a great description, but just want to quickly show you that. So the depth is obviously the number of follow-up questions that you're asking here. So if we use 18, which makes it very, very specific, and then run it, then our R2 scores, our training R2 it's explaining over 99% of the variation in the data, which is great. The loss is extremely low. The R2 score for the test close to 0 either way, which is very bad. It's explaining nothing about the test data, which means it's basically turning into just guessing the 5K for everyone by just like taking an average of all the data. So that doesn't, like, even though this is making our training loss very low, then these numbers are extremely far apart, which this is what's known as the model overfitting itself. So it's performing phenomenally on the training, but it can't do anything with the test. Think of it like in school when you memorize the answers, but you don't really learn anything. So on the test, if they give you questions that you've had in class, you can rattle those off easily. But if they give you new data, then you have no idea what's going on. So if we set this to something more reasonable, like 5, and then see what we get. So it's around 31%, and training is around 37%. Okay, so now let's play with the number of iterations. This too can also be dangerous potentially, because if you set it to like 1,000, then it can start to overfit again. So you see here our loss got extremely low, but we're at about 94% for training and about 0.02%. Or, yeah, just 2%. So the last hyperparameter that I want to go through here is something called random state. So this is going to make it so that the answers aren't just, see, the scores that we get they're slightly different each time. So this is just going to make it so that it's reproducible. So this has to not only be on the model. You see, if we put this on the model, then we still get random scores. This has to be on the training data, because train test split is also, it's going to, by default, it's going to make 75% training and 25% test, but it's going to be random, the sample that it chooses each time. So that has to have a random state too. And these have to match between both the model and the split. So now if we do this, then we get the same result each time. So that is the last hyperparameter that I want to go through. That's kind of a convenience feature so that you can like collaborate with other people better. But wanted to mention it. There are better ways to figure out the hyperparameters rather than just guessing and checking. But I think that will be a future video. What I want to do right now is I want to go through the API so that we can actually start getting some scores. So that'll be the next one. So thanks for watching, and I'll see you in the next one.